Moin, I'm Mark Albrecht. I'll be your tour guide on this journey into creating an automatic animation rig. While I'll be using Houdini to create the rig in this video tutorial, you should be able to easily transfer the thought process into any creation system, any DCC that gives you access to any kind of programmed nodes or steps inside the rig. The rig we are going to create will produce automatic animation depending on the ground or environment and on the keyframe motion of your character. We will add some animation controls that will influence the way the animation is produced to allow the same rig to be used on different species or character types. The first iteration of this rig that I created for the tutorial was based on some Python nodes. The beauty of this was that I could move around the character on the screen without having put up any keyframes whatsoever. But the disadvantage is it doesn't work that reliably in Houdini. And since we're going to use Houdini, our solution will be Vex-based. I'm going to show you all the thought processes, including trial and error, that I was going through to create the final rig. So the basic idea was to keep it simple, have a body that controlled the overall world motion of my character, and then have individual rigs for each foot. This way I only had to solve the problem of moving the foot once and then just copy and paste that solution onto each foot. I was also hoping that the same solution could be applied to multipedes or bipeds or whatever. We'll see. The idea of the rig is to have each foot react on the environment based on the motion of the character. Or in other words, I want to be able, as an animator, to move the character around, and I expect the feet to move as if they were transporting the character. So that means I have an initial animation state where I move the character, but the foot is on the ground. Nothing is happening, the character is moving forward. Then, at some state that I have to define, the foot is being lifted up into the air, moves forward while I'm still moving the character, touches the ground again, and seems to propel or push forward the character. That leaves me with at least two animation states. One where the foot is on the ground and I'm only moving the character, and two where the foot is being moved through the air, and this is the animation that my rig has to create. Obviously, I need an IK solver rig, because I have a situation where the foot is nailed to the ground or some environment and I move the rest of the body and the leg is following this motion with the foot on the ground. Luckily, creating an IK rig in Houdini is straightforward. Just click on the Bones tool, give your rig a name, I'm using leg for obvious reasons here, and select a solver type of inverse kinematics. Then you draw out your leg. The starting point is the root position, and the endpoint will be the foot. I'm going to put the basic leg rig into a network box, and that is for two reasons. One is convenience. Copying and pasting a box, a single node, is much easier than copying a whole network. And two is, if you have a look at the IK solver, these links in here that the solver needs to work properly don't always get updated correctly if you rename or move stuff around. And by having them in a network box, in a sub-layer, so to say, you basically avoid that problem. With the basic rig setup, we now need a proper place that we can find again to store the information about the animation that we're going to create. Like I said before in the scribble, we have at least two animation states, and we need to store the information which state we're in somewhere. For this, we are using an attribute. A very short excursus on this attribute solution. If you're familiar with Houdini, you can safely skip to the next chapter. When using something like Fabric, you could just create a variable and have that available throughout the timeline, no problem. But in Houdini, every frame is being evaluated on its own, so information that you stored in an attribute, which is the right place to store information, gets lost. The solution for this is to copy information from the previous frame into the current frame. And for this, you use a solver node in Houdini. You use a solver node every time that you want to iterate on information from the previous frame. To illustrate this, let's create a counter. I already created an animState variable, and I can add a code node named attrib_wrangle, where I simply increase the value of animState. every time that this node gets evaluated, which is in Houdini every time that I advance the timeline. But since the attribute create node also gets evaluated every time I advance the timeline, I always start at 0, increment to 1, and stick there. By adding a solver node, I get access to the previous frame, coincidentally called previous frame in the solver node. Now, that's strange. Now I add my attribute wrangle with a code that increments anim state by 1 every time this node gets evaluated, and I play on the timeline and nothing happens. Okay, this is a specific in Houdini. You have to step outside the solver node and then activate the solver node and play with the timeline, and all of a sudden a happy count can count. This looks good. It looks like we laid out the fundamental way of dealing with variables and transferring values from one frame to the next. So the second basic functionality we need to figure out is how to move stuff around. Looking into the documentation and on forums, you get the impression that the attribute named position, or P, is what moves geometry around. So let's try this. We add to the solver attribute wrangle an increment on the x value, on the x-axis of our point position. But if we play the animation, nothing happens at all. However, the spreadsheet seems to indicate that the x value is getting incremented. So what's going on? The problem is that the bone is not actually using the point position as its position, but it has its own transform. And the transform, the position on the bone itself, is what we need to change. Okay, then let's do that. There is a function called point that reads out a point attribute, and that is exactly what we need. We have to specify the path to a node where this attribute exists, and this is in the wrangle node inside the solver. Then we have to give the index of the point inside that node, which is the first point, so it's 0. Then we have to give the attribute's name, which is position, or P. And finally, we have to specify which channel, X, Y, or Z, on a 3-dimensional vector we want to read out. Since we're using X here, we just specify 0 for X. Let's try this out. It's a bit hard to see, but if you look at the position value, you can see that whenever the timeline advances, the X position gets incremented. Hint for the faint at heart. This is not the final version. This is trial and error. This is me figuring things out. Now it's time to lay out the code and to get something that we can check our theories on. Like I said, we have two animation states. We have anim state 0, where the foot is on the ground, and we have anim state 1, where the foot is moving, and this is the most interesting part where we have to do stuff. Since we're moving the character on X and Z, let's move the foot up into the air for starters, just to see what's happening. While the foot is on the ground, we have to somehow check if we have to start the foot lifting and the animation stuff. We are going to do that by checking some distance between the foot and the root of the leg. In order to get a 3-dimensional vector that we can use for calculations, I read out the 3 floating point values for X, Y, and Z from the position parameter, just like I would do in linking the parameter to something else. You can even use the copy parameter and paste reference in the code window. Let's do that. So we have the correct path, and then combine all that into a vector. When debugging code, you often have to print out values to check if they match your expectations. And there's a simple command to do that. It's called printf. The distance value I'm interested in is the difference between the foot current position and the leg's root. So I'm going to use printf to check the distances that I'm calculating and see if I get the results I want. This seems to look nice because we're getting changing values, but it's not really helpful. The distance seems to increase the closer the leg root is getting to the foot position. And that is because the foot is sitting in local space 0, 0, 0. We don't have access to its actual world position. So if we move the root position away from the real world 0, 0, 0, we are getting an increased distance. And that's not what we want. We want to read out the world positions of both elements. One way to get world positions for both items is to do exactly the same. That's reading out the channels on the transform parameter of both items. These are still strange values, but that's because the foot still has its local position. Its actual world position is stored in the pre-transform. If we extract the pre-transform, we get perfectly sensible data. Now it's time to create user-definable values that we can use to manipulate the way the animation is created. For starters, we need the distance that will trigger the lifting of the foot. Then we need the height that we're going to add as a maximum value to the lifting. And the third parameter that we're going to create is a step size, which will in some way define the speed with which the foot is progressing. Let's bring up the parameter editor and create a third folder so that we can visually separate our own variables from the default ones. Then we create 3 floating values, give them some telling names, and also add some sensible default values. And finally, we need to introduce the variables into our code. We can count how many times we have to step upwards. This is 5 times. And then just do the tedious task of typing in all the parameter names. With the variables introduced into the code, we can use them to trigger the animation state from 0, which is foot nailed to the ground, to 1, lift off. And what this lift off is going to do, we have to check next. Back to the drawing board. So what's happening now is that we're still moving the spider, character, whatever, along some path. And we have to find that the leg is stretching away from some position because of that movement. Again, the foot is nailed to the ground, so the distance between the foot and the leg root is increasing. But where are we going to move the foot to, and at what speed? One idea to move the foot along would be to just copy the direction that the character is currently moving in. To get that direction, we would store the previous position of the body, or the root, doesn't matter, and then subtract that previous position from the current position. That would give us a direction vector that we could use for the foot. So we would move the foot along the same direction that the body is moving. However, in order to make this video end at some point, I'm not doing this. I'm going for another solution for finding the direction of the foot movement. The problem, just in short, with copying the body direction is either you define the direction once when lifting the foot and then ignore all body movement changes or direction changes, and that will very often move the body across the path of the foot, and that looks just stupid. And the other way is to constantly copy the body direction, and that makes the foot kind of stick to the original movement of the body, and that looks extremely unnaturalistic. Instead, we are going to use a rest position for the foot for finding the target position. The advantage here is that this rest position is pointing away from the body, and that just gives enough distance from the body, even if the body is moving towards the foot, to create a much more realistic and naturalistic look. Anyway, if you don't believe me, just try it out. Store the body position in an attribute and use that attribute from the previous frame to calculate the current body direction. Copy that over to the foot. What I'm going to do in the video now is to create a rest position for the foot and use that rest position, that current rest position, as the target for the direction vector of the foot. As for the speed, we defined a step size, and one way to use this step size is as a speed, as a distance that's being covered on each frame. The advantage is that we have direct control over the speed of the animation, and the disadvantage is that this speed is global for all of the animations. So we could still keyframe it, of course. The better looking way that I found out is to define the number of steps that the foot needs to reach the target from its lift-off position. This means that if the body is moving slow, the motion will be finer, there will be shorter distances covered between frames, and if the body is moving fast, then automatically the foot will cover a lot more ground. Plus, this solution also creates some very nice overlap of foot motion and body motion. We'll see that in the end. Let's get going with the rest position. This is pretty straightforward, hoping that the model that we're going to rig has been created in a way that the relaxed or modeled foot position is the biological rest position that we want to use. We just copy the foot position into rest position and delete out the code. Done. The only thing I want to change in the user interface is instead of defining a step size, I want to define the number of steps like we just discussed. Okay, and now introduce the number of steps into the code, which means we want to get the direction vector from the rest position of the foot minus the current foot position. That gives us a vector. And this distance, this direction vector, we divide by the number of steps. Like I said, the number of steps defines how fast the foot is progressing from its stretched position to the target position that we read out from the rest position. And finally, we need to actually do that, read out the rest position and create the rest vector from that. There's quite a bit of code cleanup that we have to do, and we will continue with that in a bit. But for starters, let's remember that in Houdini, there's a difference between a local variable and an attribute. An attribute will always have an @ sign in the variable name. So if we want to have a value being stored across the frames, we have to make sure that the variable name has an @ sign in it. So if we want to update the anim state, we have to make sure that we use I for integer and @ for attribute and update that. I think that's a common cause for errors, allowing the code to have local variables and attribute variables using the same name, only differentiated by the @ sign. And since we want to store the direction that we just calculated for the foot, we have to make that an attribute as well. And to make things clean, we add this attribute direction to our attribute list. Then we also make sure that we are updating the attributes instead of the local variables, because again, only the attributes get written out and can be reused on the next frame. So far, our code should be able to nicely move the foot forward along the body motion, targeting the rest position. But we also want to move the foot upwards into the air and then down again. Let's see, within the number of steps that we have available for the animation, we have to cover both the upwards motion towards maximum height, also given in the animation parameters that we defined, and ground position. For the moment, we just use 0 for that. For simplicity, we'll just define that for the first half, we are moving up, and for the second half of the steps, we're moving down again. We can adjust that behavior later on, but let's keep it simple for starters. The task we have to solve now is to figure out whether we're going up with the foot or down. And staring at the code, it seems like we could introduce an animation state 2, so that 1 would mean we're going up and 2 would mean we're going down. However, that would mean that we have to constantly compare the current height position or Y position of the foot to some previously stored maximum height value. And if we're going to store another variable anyway, there's a much better way to do this. And that's just count in which step of the maximum number of steps we're currently in. Why would be storing the step index be better than comparing the height? The answer to that is a bit of forecast to an improvement that we're going to make later on. Right now, for simplicity reasons, we're dividing the animation by 2. For the first half, we're going up. For the second half, we're going down. If we want to change this behavior later on and shape the animation by making the upward motion faster and the downward motion slower, or the other way around, we have to know which step we are in anyway, meaning we have to store the step index. Right, now let's take care of the code cleanup. Like I said before, we have to make sure that we store all the values that we need for the next frame into attributes, because we cannot access the local variables again. One of the values that we need to carry over is the foot position. So let's write a vector attribute foot position and put the value of the local foot position into that. Have a look at the spreadsheet. This is the foot position that we want to carry over. Since the solver copies over values from the previous frame, we obviously need some animation to have the timeline running. That's what we're going to do. Let's grab the root of the leg and create a very simple back and forth animation on that. Create a keyframe on 1 for the root position, and then move to, say, something like frame 48, something like 2 seconds, and hope that the position gets stored. Nope, I forgot to set up auto key, so let's redo this. At the same time, make sure that we're using real time so that we can actually see what's happening. Clickety-click, let's start the animation and see if we got a complete failure. The foot isn't moving at all. Right, we didn't actually tell the foot to read out its position from our foot position attribute that we created. To read out the position from the attribute, we can use the point function. So point, then the path to the node that carries our attribute, the index of the point inside that node, the name of the attribute, which is foot position, and the index on that attribute. 0 for x, 1 for y, and 2 for z. In theory, this should work fine, because it did work before, didn't it? This does not look too good. Assuming that we set up our distance threshold the right way, this doesn't work. There's an exclamation mark, and the error message isn't really that telling. But to cut things short, the explanation is Houdini doesn't like any kind of recursions. What we're trying to do and failing in doing so is we try to calculate the current frame's foot position based on variables that include the current frame's foot position in some way. At least that's the way Houdini sees it. Doesn't work this way in Houdini, so we have to rethink how to deal with the foot position. The theory is right, the idea is good, the code in general is correct. We only can't read out the foot position and write it back inside the same frame. That's iterative and Houdini doesn't like it, so we have to rethink this step. But actually, we don't need to read out the foot position ever, because we do have the rest position, which in the beginning of the animation is identical to the foot position that we want to have. So to avoid reading and writing the same parameter, we just use a different parameter. In this case, we use the rest position for the start position, and then we do all the calculation based on our animation system. Okay, I wouldn't get that myself. Let me draw it out. What do we have? We have an integer named animState that defines whether we're locked to the ground or are in motion. Then we have a direction that only defines the direction and the speed that we're going to. it doesn't really store any position. It's only giving a direction and a speed per step. Then we have the step, which defines where inside the animation from the previous resting position towards the next resting position we are. And it also defines whether we're going up or down. And finally, we have the foot position. But this foot position never ever defines an actual rest position. It only uses the rest position to find the next target. So we never have to read from the foot position anyway. We can always write to it. And that's what we're doing in the next iteration. Every time I run into a dead end, or whenever I feel like, okay, now I know what to do and everything I did so far was rubbish, I like to restart from scratch. So this time I'm going to use the rest position node and recreate all the attributes that I need, the anim state, the foot position, and the direction, and the current step number or index. And then I'll create a new wrangle from scratch, because now I know what to do. Most of the code looks identical to the version before. I'm just rewriting it from scratch because I just love to practice typing. I could do the calculations on the attributes instead of copying the values over into local variables, and then in the end of the wrangle, copy the values from the local variables back to the attributes. But A, I feel more comfortable without having to type the @ sign into the variable name, and B, there sometimes are situations where you can't really deal with the attributes directly. So C, it's just more convenient to me to use local variables instead of attributes. I'm also commenting the code more than before, and that's something I can't stress enough. Do yourself a favor, or more precisely, do the instance of yourself from 10 years in the future a favor, and at least give you a glimpse of the ideas that you had in mind when you were writing this code. You don't have to comment every single line, but put some kind of structure into what you're writing. It makes things much easier to understand if you forgot everything about the ideas. Don't forget to write back the values from the local variables into the attributes, else you wonder why you have nothing to work from in the next frame. And I'm saying that for a reason. Now it's debugging time. This animation doesn't really give the result that I'm after. So maybe the values that I typed into the parameters are wrong. I don't know. Let's have a look. Printf can give us the calculation results. And just for safety, let's also output the animation state, because I don't see any change to the foot at all. Maybe anim state 1 doesn't get set correctly, although we'll see. Okay, anim state gets set on every frame. That's just plain wrong. It should stay at 1. And that's the bug. I didn't put the value of anim state from my local variable back into the attribute. Let's check again. Not that much better. Anim state is 1. Foot position is whatever. I don't know, maybe it would help if we actually put the foot position into the foot. Read out the point attribute from the solver attribute wrangle, or actually the value, the attribute should be set on the solver as well, so solver is enough. Then first point, 0, and foot position is the name that we're after. Finally, 0 for X, 1 for Y, and 2 for Z. Okay, something has happened. Yikes. At least it's doing something. So what's going wrong? The foot is only moving up. It's not moving forward. Let's look at the code. Right, the first problem is we don't want to normalize the direction. Normalize would mean that the length of the direction always is 1. But instead, like we said in the scribble, the direction also includes the length, the distance between the two rest positions. Let's check again. This is better, okay, because now the foot isn't moving up to position 1 completely, which would be the normalized position, but it's turning back down. 2 more problems to solve. First, it's only moving in the right direction, and second, it's not stopping its downward motion when it touches the ground. We're going to deal with the second problem first, because that's easy to solve. In this simplified version of the rig, we're going to only check for y to be 0, because we're just defining the ground to be on 0. But first, since the foot is moving quite rapidly, let's reduce the maximum height. And Houdini 16 shows us where the 1 is, so let's say 0.3 should do it. That's a lot better. So then check for y to be 0, and if so, set anim state to 0 as well. Iterative animation checking state. This looks like a foot moving up and down. Ouch! That must hurt. Something is still wrong, and that's the other problem of the foot not moving in the Z direction. Can you spot it? The rest position, of course, has to move along with the body. But simply parenting it to the body won't help that much, because although the rest position is now moving along with the body, what we read out still is local space positions. And we need world position, because our foot position is a world position. There are a couple of ways to get the world position of the remote node. The way I'm going to do it is use the object merge that the solver node provides. And the object merge allows me to transpose the remote position data into this object. Since the rest node, in which we are right here with our solver node, is only parented to the world, nothing else, we get the world position of the rest node. Since the object merge node doesn't have any transform channels, we have to use the point attrib function to read out the second input port of our attribute wrangle. The last and final movement is yours, and that's part 1 of creating an automated animation rig. I hope it was interesting for you. Part 2 will see us refining the rig program, adding some additional magic. And in part 3, we will actually rig a model, put the bones to weights, and create the path and the path following logic for the final spider animation.